Hello, and welcome to Astronomy 100. In this video, we're going to continue our discussion of how astronomers are able to take the light from telescopes and then, of course, figure some things out. Now, in the previous video, we talked about the ability to record a permanent image of what you see through the telescope, or to record the light through a spectrometer or through a photometer to measure different things about the light. In this video, what we're going to do is concentrate on how do astronomers get the sharpest views of the objects in our universe. So just looking at an object through a telescope and having very expensive equipment that allows you to do some sophisticated things, of course, is important. But if what you are looking at is not the sharpest view, if it's a little bit blurry or if it's distorted by the atmosphere, then of course you can't learn as many things about the object. So we're going to talk about how do we get the sharpest views of the universe. What we're also going to do is talk about how we're able to see all wavelengths coming from the different objects in our universe. In a previous video, we talked about how there's more to the light than what you see with your eyes. There is light coming from the objects of our universe at many different wavelengths, many of which, of course, we can't see with our eyes. But what we're going to find out is many of those wavelengths can't penetrate our atmosphere and make it to the ground. So we'll find some solutions to that as well. So let's start with the main idea of what we call atmospheric distortion. In a previous video, we talked about how the air that we breathe, the very atmosphere of the Earth, distorts the light coming from objects in space. Some very distant star, or in this case, let's say the planet Saturn, the light that comes to the atmosphere has to work its way through the very turbulent atmosphere. And the moving turbulence of the atmosphere, the movement of the air pockets that make up the atmosphere, will cause the light to become distorted. And so when the light is distorted, even though you have a really, really nice big telescope, the light that is reflecting off of the mirror is going to come in from slightly different directions. And so as the beams of light come in from slightly different directions, it makes it so the focal point for each of those beams of light is slightly different. So what you end up getting is the light coming to a focus in a bunch of different places. So what should be a very sharp image of a star ends up being kind of distorted. What should be a very sharp image of Saturn, you can see on the bottom here, has some distortion to it. It's not quite as clear as we would hope. If you were studying the atmospheric features of Saturn, you would want to have the clearest, sharpest view to see those very small, fine details. Now, one solution to this problem is to use a space telescope. The Hubble Space Telescope orbits around the Earth, obviously in space, and so when you're above the atmosphere, then you're not suffering from the distortion effects of the atmosphere. The problem with a space telescope is they're very, very expensive. They're difficult to get into space, and then once they're in space, you have to maintain them. So if there's something that goes wrong or breaks on the Hubble Space Telescope, in the old days, we had to actually send astronauts aboard the space shuttle to visit the telescope while it's in orbit to make any repairs and then come home. And so, of course, this is very, very expensive, and it's also dangerous to humans. And there are, of course, advantages of having telescopes in space, because when you're in space, you have the sharpest view possible of any object. And the reason why is because you don't have to worry about any atmosphere distorting the view. Let me give you a couple of examples. So here's an example of what you would see of these two. It's actually the same object, but these two frames were taken by a ground-based telescope. This is the Subaru telescope, and it is an 8-meter mirror. Okay, so 8 meters, 3 feet roughly. So we're talking about a really nice big telescope, big, big bucket, gathers lots of light, sees very faint things. But this is on the ground. And so this is the sharpest image of this particular galaxy that you will get. And then the inset box is zoomed in here. So notice it's still kind of fuzzy. Now, this is not a telescope that's out of focus. This is the sharpest focus that this telescope is capable of, but it's suffering from the distortion of the turbulent atmosphere. Now go to the Hubble Space Telescope, look at the exact same galaxy, and what you'll notice is it's much sharper. So getting out of the atmosphere reduces the effects, obviously, of the distortion of the atmosphere to the point where you can see the sharpest image possible. So space telescopes are really one very, very good solution. Let me show you just one more example here. This is what's called a globular cluster. It's a cluster of hundreds of thousands of stars, and in another video we'll talk more about what these objects are. But this is a photograph of this globular cluster, and you can see quite a bit of detail. It's a very nice picture, but what you'll notice is if you want to have the ability to see really small details in this picture, you switch to the Hubble Space Telescope, and this one single little box right here is now this entire frame. And notice that you can actually see an enormous amount of detail inside of that little tiny region of this cluster. And the circles are circling around objects that are called white dwarfs, and they were studying white dwarfs. So notice these little white dwarf objects. These are dead stars. You would never even be able to find those if you were stuck with this image here on the left. So space telescope definitely is a solution. But as I mentioned, the problem is that space telescopes are expensive, they're difficult to repair, and of course they're only as big as your rocket can be, and you can't build very, very large telescopes to put into space if your rockets are not very big. So there's a solution that actually started a few decades ago, and it's just a technological solution. What astronomers realized is we're at the mercy of a turbulent atmosphere. We can't fix that unless we go above it. But what if we were to take a mirror and had the ability to distort a mirror so that the distortion of the mirror can be the exact opposite of the distortion of the atmosphere? So that what happens is the light that will now come in distorted reflects off of this distorted mirror, and it cancels out the distortion caused by the turbulent atmosphere. So let me show you how this works. This is a type of technology called adaptive optics. So optics is obvious, it's the optical instruments. Adaptive means you adapt to the turbulence of the atmosphere. Now the way that it works is this is an instrument that is attached to the telescope along with your instrument that you're going to use to record or analyze the light. So what happens is the light will come in through the telescope and the light is distorted. Let me show you what I mean. So the light that comes in is distorted, but then what happens is there's a mirror that is used that is what's called a deformable mirror, meaning it's a mirror that's not rigid, it's a mirror that flexes. And there's actuators that are attached to the bottom of the mirror, and these actuators will push and pull various parts of the mirror. And as they push and pull the different parts of the mirror, they deform the mirror shape. Now the idea is to deform the mirror so that it is the proper shape to take the light that is coming in distorted and force the light to come to a perfect focus. So what you'll notice is, even though the light is coming in a distorted fashion, the deformable mirror will basically solve that or counteract that problem, constantly keeping the light at a perfect focus. So the light comes in, it bounces off this deformable mirror, and then eventually that light is now perfectly crystal clear, high resolution light that gets recorded by your instrument. Now, part of the light is redirected back into a system that will analyze the distortion, and it will constantly make corrections. So it's a closed loop system where the mirror is constantly changing based on the changing nature of the atmosphere. You want your mirror to change with the changes of the atmosphere. So the computer is actually doing this about 1,000 times a second. It's analyzing the atmosphere and making these changes over and over and over again, keeping the image just very, very steady. Now, by using this technology, let me show you some examples. The distortion of the atmosphere gets canceled out, and the images are quite spectacular. Here's a before and after. So this is the best resolution, or the clearest image you could take without adaptive optics. If you then make the system turn on, you now employ the adaptive optics and the deformable mirror, notice the clarity change. So this is the best you would get without it, and notice how very, very clear the image of these stars becomes once the system is turned on. You would have a hard time having any information about the details of these stars right in here. You can't even see them so well, can't see them individually. But with the adaptive optics system turned on, you can see quite a lot of detail. So it's a huge improvement. Let me show you a couple more examples. This is the image of a star without adaptive optics turned on. And then when they turn on the system, notice the clarity, absolutely crystal clear. And so anything that is associated with this star, maybe a planet or something that goes around this star, now becomes apparent, whereas before it would have been lost because the image is so distorted. So adaptive optics can do quite a tremendous job of improving the clarity. Here's one more example. This image was taken by the Palomar Observatory 200-inch telescope, and this is an image of what's called a planetary nebula. And again, this is as clear as it gets without adaptive optics, but when they turn on the adaptive optics system, you can see the clarity changes tremendously. So again, the idea is you are deforming a mirror to match and counteract the turbulence of the atmosphere. Now, one last thing related to this is, so how do they actually do this? Well, what you do is you hope to have a star near the object that you're studying, and then what you do is you constantly analyze the light from that star, and you deform the mirror in the same way that that star's light is distorted. But sometimes there's no nearby star that's convenient that can be used. So the way they solve that is really very fascinating. What they do is they attach a laser, a very, very powerful laser, to the telescope. And then what they do is they send a laser beam up through the telescope, and they actually shoot the laser beam up into the sky. And this laser beam will actually go very, very high into the atmosphere. And when the laser beam goes really high into the atmosphere, the laser light will reflect and scatter off of the molecules in the atmosphere. This is usually maybe 50 or 60 miles up. So when the laser light goes and scatters off of the particles in the atmosphere, it's as if you have created an artificial star. Now, because this is a part of the atmosphere that's turbulent that you're projecting your laser beam on, this will allow you to, again, examine the turbulence of the atmosphere and make any corrections. So the idea is that if there's no star conveniently near your object that you're going to study, what will happen is you can make your own star, an artificial guide star, and so the telescope can continue to use the adaptive optics system. So some of these big telescopes around the world have very sophisticated adaptive optics systems, and in some of these photographs it looks like they're shooting laser beams at the objects that they're studying. This is not the 200-inch telescope trying to destroy the asteroids that are coming towards us or the alien spaceship that's on its way. This is the creation of an artificial guide star that is now used with the adaptive optics system. So it's a great solution. Now, the final topic I want to talk about is the atmosphere not only distorts light, but one of the problems is the atmosphere does not allow all wavelengths of light to penetrate it. So just very quickly here is the electromagnetic spectrum from radio waves all the way to gamma rays. And what this graph is showing down here is what's called atmospheric transparency. So what that means is if the line goes all the way down, that means that these wavelengths can go all the way to the surface of the Earth. And so in radio wavelengths, the atmosphere is completely transparent to radio light. So you can have radio telescopes on the ground, and any object in our universe that produces radio light, that light can be seen, and we can have ground-based telescopes. But notice when we get up into the microwave, the atmosphere starts to become essentially opaque to microwave wavelengths. You can't see microwave light on the ground coming from space because the microwave light doesn't go through the atmosphere. It's blocked by the atmosphere. Infrared is blocked by the Earth's atmosphere. Some of it makes part of the way down, but you'll notice that the infrared light doesn't make it to the surface. So an infrared telescope on the surface of the Earth isn't going to do you any good. Infrared light just doesn't make it to the ground. Notice in the visible portion of the spectrum, all of it makes it to the ground, so optical telescopes can be ground-based telescopes. But then once you get to ultraviolet, X-ray, and gamma ray, all of these wavelengths never make it to the ground. which is a good thing because ultraviolet light, X-ray light, and gamma ray light is actually very deadly to life. So our atmosphere actually absorbs these deadly wavelengths of light. So if you're going to study these wavelengths, you have to have a telescope in space. Sometimes you have no choice. You just have to have a telescope in space to be able to analyze the wavelengths you can't see from the ground. So as you can see, there's ways to take away the distortion of the atmosphere, and there are ways to make it so that the opaque nature of the atmosphere can be fixed by simply going into space. All things that have to be considered by astronomers. In the next video, we'll continue our discussion. I'll see you then.